Question number 20. A beam with symmetrical T-shaped cross-section as shown in the figure is subjected to pure bending. The maximum magnitude of normal stress is realized. Option A, only at top fibers of the cross-section. Option B, only at the bottom fibers of the cross-section. Option C, both at the top and the bottom fibers of the cross-section. Option D, only at the centroidal fiber of the cross-section. Right, so bending stress formula, we know that sigma is equal to plus minus m by I into y. So as of now we will forget this because they are asking magnitude here, maximum magnitude of normal stress. In this formula, this y is the distance from centroid, right? Larger is the distance from the centroid, more will be the bending stress, correct? So for T section, its centroid will lie closer to the top fiber, let's say here, right? Closer to this top fiber. So this distance, that is this y bottom, will be more than this distance from the centroid, y top. So larger is the distance from centroid, more will be the bending stress, correct? So here bottom fiber is lying far away from the centroid. It means that maximum magnitude of normal stress will be at bottom fiber here, right, at bottom fiber here. So option B, only at bottom fiber of the cross section, is correct. Question number 21. A 3-member truss is simply supported at Q and R, so here and here, and loaded at P by horizontal force as shown. The force in QR is, we have to find out force in member QR. So for this question, if you have attended the class and listened the lecture properly, then you don't need to pick up the pen also to solve this. See, this roller support cannot provide any horizontal reaction, and we are applying horizontal force F here, right, horizontal force F. So the complete reaction will be offered by support Q, that will be opposite to the applied force, like this F, right? Now in lecture we saw that the best method is to consider the joint and resolve the forces, right? So if you resolve the force horizontally at point Q here, then it will be directly equal to F, right, force in member QR. So it is force F tensile. So force QR will be equal to force F. Question number 22. The closed thin-walled rectangular channel shown in the figure 1 is opened by introducing a sharp cut at the center of the bottom edge as shown in the figure 2. Which one of the following statements is correct? Option A, centroid of 1 and 2 coincide while shear centers do not. Option B, shear centers of 1 and 2 coincide while centroids do not. Option C, centroids and shear center of 1 and 2 coincide. Option D, neither centroids nor shear center of 1 and 2 coincide. So for figure 1, it is symmetrical about both axes. So its centroid will lie on intersection of plane of symmetry here, right, and its shear center will also lie here only because it is symmetrical about both the axes. So for figure 1, centroid and shear center coincide at one point only. Now coming to figure 2. For figure 2, the area distribution is symmetrical. It is sharp cut. So centroid will lie at same position here. Correct? But because there is cut, now it is open section, and due to this, its shear flow distribution will be different than this closed section. Right? It means that its shear center is not going to lie at this position, at centroid. Right? So its centroid and shear center will be at different point. And moreover, in the lecture, we studied this type of open section for which shear center was somewhat here, correct, and not at the centroid position. So it lies outside the body, right? So here what it is, like this and like this. So it is not going to be at this point where centroid lies. Now in option A, centroid of 1 and 2 coincide while shear centers do not. So this is the correct option. Question number 28. Let sigma and tau represent the normal stress and shear stress on a plane, respectively. The Mohr circle that may be possibly represent the state of stress at point in a beam of rectangular cross section under pure bending is R. So Mohr circle is given. We have to find out which Mohr circle represent the stress under pure bending. So for pure bending, let's say this is the beam and we are applying bending moment like this. Bending moment M. So bending stress due to this bending moment will be M by I into Y. Correct? Now on top fiber there will be tensile stress. Here it will be tensile positive. On bottom fiber it will be compressive negative. Compressive stress, right? And on neutral plane, let's say this, there will be no stress. Now let's talk about the fiber which is above the neutral axis, right? This neutral axis, above this neutral axis. So for that, case 1, above the neutral axis, sigma x is non-zero, it will be positive, correct? Sigma x will be greater than 0, positive tensile stress for the fiber which is above the neutral axis for this bending moment. What about sigma y? 0 and tau xy 0. Now let's talk about the fibers which is below the neutral axis for which sigma x will be compressive, right? So this is sigma x, here it will be compressive. So for case 2, sigma x, again it is non-zero, but this time it is negative because it is compressive. Sigma y again 0, again tau xy is 0. Now for case 1, let's find out Mohr circle radius and its center location. So radius, we know the formula, r is equal to sigma x minus sigma y divided by 2 whole square plus tau xy square. This is the formula to calculate the radius of Mohr circle. So for case 1, r is equal to sigma y is 0, tau xy is 0, so it will be sigma x by 2, right? What about center location? The formula to find out center location is sigma x plus sigma y by 2 comma 0. So sigma y is 0, so its center location will be sigma x by 2 comma 0, right? So Mohr circle radius is sigma x by 2 and its center is located at sigma x by 2 only. So let's draw the Mohr circle. Let's say this is sigma axis and this is tau axis. So its center is located at sigma x by 2, let's say here, and its radius is also equal to sigma x by 2. It means it will be tangent to tau axis. Like this, right? So this is for case 1, means for the fibers above the neutral axis. Now for case 2, for the fiber below the neutral axis, sigma x is negative, sigma y is again 0, tau xy is again 0. So for case 2, radius of Mohr circle is equal to again sigma x by 2 and center location will be minus sigma x by 2 comma 0. So again we have used same formula. This is for the radius, tau xy is 0, sigma x is negative, so square of this will be positive only. So sigma x by 2 will be the radius again, and location of center is given by sigma x plus sigma y by 2 comma 0. So sigma y is 0 and it will be equal to minus sigma x by 2. So let's draw it on Mohr circle. Again this is sigma axis and shear stress tau here. So center location is, let's say here, at minus sigma x by 2 and its radius is also equal to sigma x by 2. So again it will be tangent to shear stress axis. So let's draw. So this will be the Mohr circle for case 2, means for fiber which is below the neutral axis, and there will be compressive stress. Now let's see the options. So we got this and this. So both B and C are correct options. Question number 29. An isotropic linear elastic material point under plane strain condition in the xy plane always obeys. So plane strain condition, correct? That also in xy plane. So we know that for plane strain condition in xy plane, all the strain component in z direction will vanish, right? So linear strain in z direction, epsilon zz is equal to 0. Shear strain xz is also equal to 0. Shear strain yz is equal to 0, and because it is isotropic material, tau xz will also be equal to 0, because tau xz is equal to g into gamma xz. So it is 0, so it will be 0. Similarly, tau yz will also be equal to 0. Linear strain, shear strain 0, shear stress 0. What about normal stress sigma zz? It will not be equal to 0. Why? If we write the expression, linear strain in z direction is equal to sigma zz divided by E minus mu divided by E sigma xx plus sigma yy. This is 0 according to the plane strain condition. So sigma zz by E is equal to mu by E bracket sigma xx plus sigma yy. This will get cancelled out. So sigma zz is equal to mu sigma xx plus sigma yy, which is not equal to 0, correct? Because sigma xx and sigma yy are not equal to 0 in this plane strain condition. Now let's see the options. Out of plane normal strain is 0, correct? Out of plane normal stress is equal to 0, no, it is not equal to 0. Just now we saw this. Out of plane shear stress is 0, correct? Out of plane shear strain gamma xz is 0, so it is also correct. Means option A, option C and option D, these are correct option, right? Question number 33. The two-dimensional plane stress at a point is sigma xx is given, sigma yy is given, tau xy is given. The normal stress sigma n on a plane inclined 45 degree as shown in the figure is. So we have to find out normal stress on this plane inclined at 45 degree. So we know the formula to find out normal stress on any plane inclined at any angle. What is that formula? Sigma n is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Correct? But in this formula, the angle is taken from vertical plane. This angle. So this is also 45 only. So let's substitute the value. Sigma x 110 megapascal. So let's leave it in megapascal only. We'll get the answer in megapascal. And they are also asking in megapascal only. 110 plus 30 divided by 2 plus 110 minus 30 divided by 2 cos 2 into theta, that is 2 into 45, that is 90 plus tau xy 40 sin 2 theta means sin 90. Correct? Cos 90 is 0, so this term is completely 0. This is 110 plus 30, 140 divided by 2, 70 plus sin 90 is 1, so it is 40. It is equal to 110 megapascal. So this was very simple question. The answer is 110 MPa. Question number 41. A horizontal force F is applied at point R on a two-member truss as shown in the figure. Both the members are prismatic with cross-sectional area A0 and made up of same material with Young's modulus E. The horizontal displacement of point R is. So we have to find out horizontal displacement of this point R and we are applying horizontal force F. So we know that displacement, let's say del, is equal to rate of change of total strain energy with respect to the load applied F. Correct? So first we have to find out total strain energy. So what is U, total strain energy? U is sigma square by 2E into volume, right? This we have studied. So sigma we can write load upon area. Let's say load is P. So P square by A square into 2E. Volume is area into length. This will get cancelled out. We will get load P square upon 2AE into length L, right? So this U we have to find out for each member, that is RQ and RP. So first of all we have to find out length of this member. So length, how we can find out? This is 90, right? So from here we can write RP sin 45 is equal to L. So RP will be equal to under root 2 L, and that is equal to RQ, right? So we found the length of the member, which we will substitute here. Now let's find out the force in these member. So how we can find out? So let's resolve the force in vertical direction at point R here. So if we resolve the force in vertical direction, summation of vertical force is equal to 0. So force in RQ we will resolve vertically. So this is 45 and this is also 45 degree. So FRQ into cos 45 plus FRP cos 45 is equal to 0 because there is no force in the vertical direction here. So from here we got FRQ is equal to minus FRP. Now let's resolve the force in horizontal direction. So resolving the force in horizontal direction. So that will be FRQ sin 45 plus F is equal to FRP sin 45. FRQ sin 45 plus F is equal to FRP sin 45. So FRQ is equal to minus FRP, so we can substitute here minus FRP sin 45 plus F is equal to FRP sin 45. So we got F is equal to 2 FRP sin 45. So F is equal to 2 by root 2 FRP. So force in the RP member is equal to F by root 2. What about force in RQ? That will be negative of FRP. So minus F by under root 2. Now we can find out total strain energy U. Right, so that is P square into length upon 2AE. So that is equal to, so first of all for this member RP and then for RQ. So for RP, load P is, or force P is F by root 2. So F by root 2 square, length L is under root 2L upon 2, cross sectional area is A naught E, plus for RQ member minus F by root 2 square into length L, that is under root 2 small l upon 2 A naught E, right? So U is equal to F square L by 2 under root 2 A naught E plus F square L by 2 under root 2 A naught E. So strain energy U will be equal to F square L by under root 2 A naught E. Now we can find out horizontal displacement del, that will be equal to dou U by dou F. So that will be 2F into L upon under root 2 A naught E. So del is equal to under root 2 F L upon A naught E, under root 2 FL by A naught E. In option C, under root 2 FL by A naught E. Question number 57. Given the tip deflection and tip slope for a tip loaded cantilever of length L are n L cube upon 3 EI and n L square upon 2 EI respectively, where n is the tip force and EI is the flexural rigidity. So these are known results, right? A cantilever PQ of rectangular cross section is subjected to transverse load F at its midpoint. The two cases are considered as shown in the figure. In case 1, the end Q is free. Here end Q is free in case 1. In case 2, Q is simply supported. Here it is simply supported. The ratio of magnitude of the maximum bending stress at P in case 1 to that in case 2 is. So here at P, we have to find out ratio of magnitude of maximum bending stress. So what is bending stress? In terms of moment, sigma is equal to m by I into y, right? So in both cases, moment of inertia I and this y, means distance from the neutral axis, will be same. So bending stress will be directly proportional to the moment, right? So for case 1 divided by for case 2 will be equal to directly the ratio of moment, maximum moment for case 1 to the maximum moment for case 2. So let's find out maximum bending moment for case 1. So for case 1, maximum bending moment will be F into L. Here this is L, right? So they are asking magnitude, so we are not considering whether it is hogging or sagging moment. So maximum is this for case 1. Now for case 2, this case we can write for case 2 what will be the moment at P? that is equal to F into L minus reaction RQ into 2L. Correct? Now we have to find out reaction here, reaction RQ. What will be the reaction RQ here? So we can easily find out. This type of many questions were there in test series where cantilever was simply supported at other end and we had to find out reaction at simply supported and reaction at fixed end like this, right? So we can easily find out reaction RQ. So how we can find out reaction RQ? The deflection at Q, the downward deflection here at Q due to force F will be equal to upward deflection at Q due to RQ, because there cannot be any deflection at point Q because it is simply supported, so both will be equal. So let's find out. Here F, so this will bend like this, so we can find out total deflection at Q. So under the load it will be F LQ upon 3EI, this thing. What about this? This we can find out from slope, theta into this distance L, so plus F L square upon 2EI, this will be slope under the load F into distance L. Correct? So this will be the deflection at point Q. Now because of reaction RQ, this thing, this will be simply RQ into 2 LQ upon 3EI. Right, both will be equal. So EI cancel out, L cube also we can cancel out, so it will be F by 3 plus F by 2 is equal to 8 by 3 RQ. So it will be 5F by 6 is equal to 8 by 3 RQ. So RQ, reaction at Q is 5 by 16 F. Right, now we can substitute here. So for case 2, bending moment at P will be equal to F into L minus RQ into 2L. So 5 by 16 F, this is RQ, into 2L. So FL minus 5 by 8 FL equal to 3 by 8 FL. So bending stress sigma 1 divided by sigma 2 is equal to M1 by M2. So M1 is FL, M2 is 3 by 8 FL. This will get cancelled out. It will be equal to 8 by 3. So the bending stress at P for case 1 divided by bending stress at P for case 2 is equal to 8 by 3, 2.7. Question number 58. A simply supported aluminium column of length 1 meter and rectangular cross section W into T with T less than equal to W is subjected to axial compressive loading. Young's modulus is 70 GPa. Yield stress under uniaxial compression is 120 MPa. The value of T at which the failure load for yielding and buckling coincide. So it is simply supported. So buckling load for simply supported is P is equal to pi square EI upon L square. So they are asking that we have to find out value of T at which failure load for yield and buckling will coincide. So if we divide it by area, it will become stress. Both side division by area, it will be stress, and this should be equal to yielding stress, that is 120 MPa. So it is 120 into 10 raised to power 6 is equal to pi square into E 70 GPa. So 70 into 10 raised to power 9 into I. In buckling, the moment of inertia is the least moment of inertia. Here it is clearly mentioned that T is less than equal to W. It means least moment of inertia will be W into T cube upon 12, right? Let's say, for example, this is the rectangular cross section and this is W and this is T, right? So it will be BD cube by 12, that is W T cube by 12, right, divided by area, that is, what will be the area, W into T into L square. L is 1, correct? W and W will get cancelled out. So we will get 120 into 10 raised to power 6 upon pi square into 70 into 10 raised to power 9 is equal to T square by 12. So this will be 2.084 into 10 raised to power minus 3 is equal to T square. So T will be equal to 0.04565 meter. Now they are asking in mm here. So this will be equal to T is equal to 45.65 mm, right? Question number 59. A 0.5 meter long thin walled circular shaft of radius 2 cm is to be designed for an axial load of 7.4 kN and torque of 148 Nm applied at its tip, as shown in the figure here. The allowable stress under uniaxial tension is 100 MPa. Using maximum principal stress criteria, the minimum thickness T of the shaft so that it does not fail is, in mm we have to find out. This is thin walled circular structure. So both axial load and torque is acting on this structure. So let's find out normal stress due to axial load first of all. So sigma x is equal to P by A, that is 7.4 kilonewton 10 raised to 3 upon area. What is the area of thin ring? Pi dt, right? 2 pi RT. So let's substitute R value. 2 pi into R is 2 centimeter here. So 0.02 meter into T. Correct? So sigma x will be equal to 58887.33 upon T. So we will get stress in terms of thickness T, because T we have to find out. Now let's find out shear stress due to torque of 148 Newton meter. So shear stress tau is equal to torque upon J into R. So torque is 148. J is polar moment of inertia of this thin ring, that we already know, that is 2 pi r cube T, correct, into R. So this polar moment of inertia is known result. So we are not proving here that how polar moment of inertia of the thin ring is 2 pi r cube T. So 148 upon 2 pi into 0.02 square into T. So tau xy is equal to 58887.33 upon T. Means both sigma x and tau xy, both are same, right? Now let's apply the criteria. They are telling to use maximum principal stress criteria. So what is maximum principal stress criteria? That maximum principal stress should not exceed the allowable stress in uniaxial tension, that is 100 MPa, correct? So sigma 1 should be equal or less than 100 MPa. So let's find out sigma 1. So sigma 1 is equal to, we know that formula, sigma x plus sigma y divided by 2 plus under root sigma x minus sigma y by 2 square plus tau xy square. So sigma y is 0 here also. So sigma 1 is equal to sigma x by 2 plus under root sigma x by 2 square plus tau xy square. So both sigma x and tau xy are same, so we can take common. So sigma 1 maximum principal stress, let's take sigma x common because sigma x is equal to tau xy, half plus under root 1 by 4 plus 1, right? So let's substitute sigma x value and sigma 1 100 MPa. Sigma x is 58887.33 upon T. So 100 into 10 raised to power 6 is equal to 58887.33 upon T bracket half plus under root 5 by 4, right? So it will be 58887.33 upon T into 1.618 95281.7015 upon T is equal to 100 into 10 raised to power 6. So T is equal to 95281.7015 upon 10 raised to power 8. So thickness T is equal to 9.52 into 10 raised to power minus 4 meter. But they are asking in mm, so T will be equal to 0.952 mm, right? But they are asking round off to nearest integer. So T will be equal to 1 mm. Question number 60. A 10 kilonewton axial load is applied eccentrically
on a rod of square cross section 1 cm cross 1 cm as shown in the figure. The strains measured by the two strain gauges attached to the top and bottom, they have shown here, surfaces at a distance of 0.5 meter from the tip are, so strains are given. On the top it is 0.0016, on bottom it is 0.0004 respectively. The eccentricity in the loading E is in mm. So load is not applied at center, it is applied at some eccentric distance from the center, right? So let's shift this load to the center. When we will shift this load to the center, let's say load P is equal to 10 kilonewton. Then one moment will also come, right? Because here it is not acting at center. So when we will shift this load 10 kilonewton to the center, one moment will also come. M is equal to P into E, right? 10 kilonewton into E. Now stress on any fiber will be due to two things. One, due to normal stress due to axial load, and second, due to bending stress due to the moment M, right? So for normal stress, that will be P by A. Bending stress, we know that how stress varies in bending. Sigma is equal to M by I into Y, where Y is the distance from centroid. So its cross section is also given, right? So its centroid will lie here at the center, right? So Y distance for the upper fiber is 0.5 and for lower fiber also it is 0.5, correct? Now stress on the top fiber will be due to two things. Normal stress due to axial load, that is P by A, plus bending stress, that is M by I into Y. On the bottom fiber, sigma 2, let's say this is sigma 1, it will be again due to normal stress minus M by I into Y. Why minus? Because on the top fiber it will create tensile stress, on the bottom fiber it will create compressive stress, right? This kind of moment. Upper fiber will be in tension and bottom fiber will be in compression. Now if I want to find out strain on the top fiber, then we can divide stress by Young's modulus of elasticity. That will become strain. Similarly, here on the bottom fiber, right? This is equation 1, this is equation 2. Let's divide this. E and E will get cancelled out. We will get this ratio. Strain on top fiber divided by strain on bottom fiber is equal to P by A plus M by I into Y upon P by A minus M by I into Y. Now let's substitute the values. P is equal to 10 kilonewton, right? Strain on top fiber is 0.0016. Strain on bottom fiber is 0.0004. 0.0016 upon 0.0004 is equal to, let's put the load in kilonewton and dimension in centimeter only for simplicity of calculation. Then moment we will get in kilonewton centimeter only, right? So P is equal to 10 kilonewton upon area 1 into 1 plus M upon I, moment of inertia of square cross section is side raised to 4 upon 12, correct, where A is equal to 1 centimeter. So 1 raised to 4 upon 12, y is 0.5 upon 10, 1 into 1 minus m upon 1 raised to 4 upon 12 into 0.5. So this will be 4 is equal to 10 plus 12 into 0.5, 6m upon 10 minus 6m. So we can write 40 minus 24m is equal to 10 plus 6m, 30 is equal to 30m. M is equal to 1 kilonewton centimeter, right, because we are using kilonewton and centimeter for load and dimensions respectively, correct. So that's why we will get in kilonewton centimeter. Now moment is equal to here P into E, right. So P into E is equal to 1 kilonewton centimeter means 1000 Newton centimeter. P is equal to 10 kilonewton into E is equal to 1000. So E is equal to 1 by 10 centimeter, but they are asking in mm. So 1 centimeter is equal to 10 mm. Answer is 1 mm. Right? Question number 61. For a thin-walled eye section, the width of the two flanges as well as the wave height are same, that is 2b is equal to 20 mm. Thickness is 0.6 mm. The second moment of inertia about horizontal axis passing through the centroid is, right, they have mentioned thin walled section. So here thickness they have not shown in the diagram, they have given thickness is 0.6 mm. So these dimensions are from center line itself. It means so this is 20 mm, this is also 20 mm, and 20 mm. Thickness T is 0.6 mm. So it is symmetrical about both the axes, so its centroid will lie here at this point. So moment of inertia I will be equal to, that is BD cube by 12. So for wave section it is 0.6 into 20 cube upon 12 for this wave section, right, this section. Now for flange it will be 20 into 0.6 cube upon 12 about its own local centroid, but we have to find out about the centroid of complete cross section, correct, about this. So we can use parallel axis theorem. So that will be area into square of this distance, right. So its area is 20 into 0.6 into what is this distance, 10 mm. So 10 square, this is for one flange,
means this. What about other, the bottom flange? Same, right? So we will just write 2 times of this thing here, 2. Now it is thin section, so this cube of 0.6 will be very small, so we can neglect this. Even if you are not neglecting, you will get the correct answer. So I, moment of inertia, will be equal to, so this term is 400 plus this term is 2400. We are neglecting this. Even if we are not neglecting, we will get the correct answer. It will vary slightly, so we can neglect it. So I will be equal to 2800 mm raised to 4, right? So they are asking in mm raised to 4 only. The answer will be this.
Question number 62. A damper with damping coefficient C is attached to a mass of 5 kg and spring of stiffness 5 kN per meter as shown in figure. Here 5 kg mass is attached to this damper and this spring. The system undergoes underdamped oscillations. If the ratio of third amplitude to the fourth amplitude of the oscillation is 1.5, the value of C is in Newton second per meter. So x3 by x4 they have given, that is 1.5. So this is the ratio of successive amplitude. We know that natural logarithm of ratio of successive amplitude is logarithmic decrement, correct? Logarithmic decrement del, that is equal to ln x3 by x4 is equal to ln 1.5, that is equal to 0.4055. We also know the relationship between logarithmic decrement del and damping ratio zeta, that is del equal to 2 pi zeta upon under root 1 minus zeta square. Let's find out zeta. So del is equal to 0.4055 is equal to 2 pi zeta upon under root 1 minus zeta square. Squaring both sides, we will get 0.16443 is equal to 4 pi square zeta square upon 1 minus zeta square. We can write 0.16443 minus 0.1643 zeta square is equal to 4 pi square is equal to 39.48 zeta square. So 39.644 zeta square is equal to 0.16443. From here zeta square is equal to 4.14766 into 10 raised to power minus 3. So zeta will be under root of this thing, so that is 0.0644. Now we got the zeta. Zeta is also equal to C upon critical damping coefficient Cc. So what is critical damping coefficient? That is 2m omega n, right? 2m omega n we can write k by m. From here we can take m inside, so we can write Cc is equal to 2 under root k m. This we can substitute here.
So zeta is equal to 0.644 is equal to C upon 2 under root km. So C is equal to 0.644 into 2 under root K is 5 kilonewton per meter. So 5000 Newton per meter into mass, that is 5 kg. C is equal to 20.36 Newton second per meter. So they are asking rounded off to nearest integer. So C is equal to 20 Newton second per meter. Question number 63. A uniform rigid prismatic bar of total mass m is suspended from a ceiling by two identical springs as shown in the figure. Let omega 1 and omega 2 be the natural frequency of mode 1 and mode 2 respectively, where omega 1 is less than omega 2. The value of omega 2 by omega 1 is. So this rigid bar is suspended from a ceiling with two identical spring of spring constant K, right? So there will be two modes of vibration. Let's see those modes. So this is first mode, in which it will vibrate like this, and this is second mode, in which it will vibrate in this manner. Correct? Now let's write the equation of motion for these two modes. Then we will find out frequency of vibration for these two modes, right? So first of all, for mode 1, m k k. So let's write the equation of motion. M x double dot is equal to minus 2k x. So mx double dot plus 2k x is equal to 0. So we can write x double dot plus 2k by m into x is equal to 0. So if we compare this equation with basic equation of vibration, then frequency of vibration, let's say omega 1 is equal to under root of this thing, correct? So under root of 2k by m, right? Now let's find out for second mode. Let's say this is theta, this is L by 2. So extension of spring will be L by 2 into theta for smaller angle approximation, correct? Here compression of spring will be L by 2 into theta, correct? So let's write the equation of motion. I theta double dot is equal to minus spring force will be K into this much distance. And what about torque about this point? This force into distance, that is L by 2, this distance, correct? So we can write force, that is K into L by 2 into theta. This will be force, but this is torque equation. So
force into L by 2 will be the restoring torque for this spring, correct? But there are two springs, so this will also give the restoring torque like this. So we will directly multiply with 2. So I theta double dot is equal to minus K L square by 2 into theta. I theta double dot plus K L square upon 2 theta is equal to 0. Theta double dot plus K L square upon 2I theta is equal to 0. Right? Now, those people who have attended the class at GATE Aerospace Academy, they might ask that why we are writing independent equation, that is uncoupled equation for mode 1 and mode 2. Why not coupled equation? Right? So answer for that question is, see, coupling depends upon the coordinate system we choose. Right? We can choose such coordinate system that will make our equation independent. Even if you write coupled equation, still you can use few relations to make that equation uncoupled, and then both equations will be independent of each other. Like here, this is completely independent of this, correct? This equation and this equation, we can solve this equation independently. So this is the answer to that question which you may ask. So let's find out omega 2. So if you compare this equation with fundamental equation, then natural frequency, let's say omega 2, will be under root of this thing, correct? Under root of K L square upon 2I. Now let's substitute the I value. Mass moment of inertia, we already know, that is ml square by 12, correct? So 2 into I is ml square by 12. This will get cancelled out. So omega 2 is equal to under root 6K by m. So let's find out the ratio. Omega 2 by omega 1 is equal to under root 6K by m upon under root 2K by m. Right? This will get cancelled out. So it will be under root 3 1.73